Okay, we did this one a little bit last week. But here we actually have like the 3 different types, typical types of radio transceivers that you might have. So this would be the mobile, and this one's set up to be used inside. It's a dual band that does 2 meters and 70 centimeters. Set up to be used inside because it has this power supply here. You can plug into a wall. This is one of the ones that we used here for our emergencies and emergency drills. Based on this station. This is more of a base station style. So this one actually, so the radio itself can cover most of the bands, at least all of the HF bands and the 2 meter and 70 centimeter band at up to 100 watts.
Is that your own?
Yeah.
What model is that?
991.
How much is something like that?
Because it's got all the things on it and does a few different other things, it's probably about 800 or 900 to 1400. But you're not expected to go out and buy one of these.
Oh, yeah.
So, and obviously, yes, you are. The hands.
Yeah, we're on
Obviously,
start-
what are the
start
handhelds?
kit.
Yeah, handy talker or handheld transceiver. These will typically be 1 to 3 different bands coverage. It's pretty common to have a 2 band, and those 2 bands being typically the 2 meter and the 70 centimeters. So, you guys remember what frequencies those were, roughly? 2 meter? Hmm?
400s.
456.2.
Oh, that's the 450-ish ones is 70 centimeter. And the
446.
and the one for 2 meter is
146.52.
under 150.
Uh,
So it's like 144 to 148. And just as a reminder, I've got this pen. What color did you say showed up well? And
Any of the bright ones.
what was it?
Any of the bright ones don't do green.
Don't do green. Don't do the ones in my hand. Okay. So one way. So remember we said like it was the speed of light is equal to the frequency times the wavelength. And that comes out to, remember we said this was 300 meters per second. 300 million meters per second. Million. I guess I should redo that. M meters per second. Frequency measured in megahertz or in hertz. And what is a hertz again? Is that something you get when you fall down?
Cycle per second.
A cycle per second, yes. And then and the wavelength is measured in meters, so it would be lambda for wavelength, measured in hertz, measured in meters, and then we had this kind of circle ratio diagram that we could use to remember that. So if we say that this is 300 and we measure our frequency in megahertz, and we measure our wavelength in meters, then we can kind of replicate this and say, oh, I need to know what the wavelength is. So he's telling me 2 meters, and I wanna know the frequency. So then what do? I take meters and divide that into 300. Or vice versa, if you see something like, hey, what band is 146.52 megahertz on? You go reverse that. Okay, so these are different types of transceivers. The difference being like how much power, one of the key differences is how much power they put out. Another one would be the number of bands it can cover. So the amount of different tuner circuits it holds in there. So you can get ones this size that will cover all the bands, but they're also not very powerful. Or this is, 100 watts is a decent amount. But if that's not enough, you can still hook this up to an amplifier to get all the way up to the 1.5 or 2 kilowatts that you're could possibly use on some of the bands. All those amplifiers are pretty darn expensive too. But yeah, so like this one will know, for example, like if I'm on one of the HF bands, it'll know, oh, you're in this section, you're probably trying to do single sideband, and it knows that like lower sideband is the convention there. And so it'll automatically set it to use lower sideband as opposed to upper sideband. Or it will use, there's it has different filters, so if you wanted to do Morse code, you could set it to use a filter so to make sure that it has a really narrow bandwidth Morse code transmission when you use it. But yeah, any questions on different transceivers? Okay, so we talked about kind of the big issues with like getting a strong signal out. One of those is your transceiver and how much power it can put out. Another one was the feed line, which we'll talk a little bit more about. And the last one is the antenna. Now we were talking a little bit last week at the end of class, like that antenna, it's not just the antenna, but it's also the antenna's placement. So what would be the optimal place to stick an antenna? On the roof, yeah, on the top of a mountain. It's all about like what it can see, line of sight. That gives most antennas their effectiveness. There's also in some of the like high frequency communication that you might want to do where you want to aim towards the horizon or up, you still want to be up a certain amount from the ground, because the ground will kind of interfere with the shape of your signal and how strong it is going out. Okay, so antenna types. Talked a little bit about some of these last time. Rubber duck he was talking about was just this cheap little short antenna on top of that comes with most HT radios. And if I were to like destroy this and peel back all the plastic, it basically would look like a spring. But they're good enough for you to just get on to transmit on the band and have a good enough match where it's resonant, but they aren't particularly effective.
And just throw them away and get a better one.
Yeah, and so an example of that would be this antenna, which is basically an improvement on this one. And I've got other radios like this that I have an antenna like this. So this one's longer and uses less of a coil and whatnot to make it seem like it's electrically longer. We were talking about that before, that like there are certain, so corresponding to the wavelength of the band that you're transmitting on, there's a certain length of wire antenna that's optimal for that. It could be the full wavelength, or it could be a certain discrete ratio of that. Like it could be quarter of the wavelength, it could be a half wavelength. At each of those, you've got some different characteristics. So while this isn't 2 meters long, it's still better than this one. And it's tuned better and a little bit longer, and so that it can, so it resonates better and lets out more power of the signal when you're transmitting. The other types, so a vertical, so these ones are also kind of an example of a vertical, right? So going straight up from the radio or straight up from the ground. Typically I hold it straight up when I transmit, I don't have to, but you've got lots of examples, like the one that's on top of this building is a vertical, just a straight up antenna. It might also have, do they have an example of the vertical on there? They don't really. It might have some radials, so it would be, so it's, you know, while it goes up straight like that, and then often it'll be like attached to a top of a pole, like that. Sometimes they'll also have a series of radials coming out like this at a certain spot. And that is because most antennas, at least the top ones here, all want to be what's called a dipole, which means 2 poles, right? Having a positive and a negative. And so you're always trying to find a mirror image for that. So that's one of the problems with the HT, small HT antennas, is they don't really have a second half. So they lose a bit of their effectiveness just by not having second half. But a lot of verticals that you see, permanently mounted verticals, will have some sort of either radials or you'll even see some verticals like, you know, like that, but say, actually I think, you can see like this right here, you can barely see it right there. But really, essentially it's an antenna that mirrors at the same distance going down the opposite direction. So it's fed here at the center for both of them, but there's an upper half and a lower half, and that technically is a dipole as well, just vertically polarized. We'll talk a little bit about polarization here in a minute. But yeah, so kind of the first antenna, the one antenna that all other antennas are measured against either being better or worse than is the dipole, the horizontal dipole, which basically means that I come out of my feed line, which is, you know, like a coax or whatever that has a center and a shield, so it's carrying essentially 2 lines in it. And I go into an antenna that's the same length on both sides, but like that. So same length attached, so one side, like maybe the center line attached to this side and the outer jacket side of that coax attached here. We'll look a little bit more into coax in a minute. But in a sense, there really is kind of, and I don't want to really call it positive, negative, but there are 2 poles to this. And when this transmits, you know, it's transmitting off of both segments of wire of the antenna, wire or poling or whatever. So something that they learned, a Japanese guy that I think his name is Yagi at some point, but if you look in the background of this picture or the picture that they have there in the center, you'll recognize that for being something like either the big huge antennas that you've seen on neighbors' houses that are ham radio operators. But also it might remind you of the kind of antennas that we used to use for broadcast TV. But what they learned was, and you can barely see this here, you can see that there's just a little bit of something coming off the center that goes off to each side of this. I don't know if you guys can see that well enough. But this is essentially a dipole antenna that then has extra elements that have been added to it. And what they discovered, what this Yagi gentleman from Japan discovered and others discovered, is that if they put these unconnected elements, so there's no, this isn't, so these are all insulated, so it's not that they're electrically connected at all between each other. The only ones that are connected to the feed line is this one right here. And they learned that, hey, the more elements that we put at a certain and they discovered that there was a certain ratio, a certain like distance depending on the frequency and all that, that if they put elements in front and some elements in back, it had the effect of focusing the signal to be stronger in that direction along that axis that they're pointing. So a Yagi is a good example, a simple example of a directional antenna. So coming out the tips, it's not very effective. And it's even, so we have same thing here with this one, not very effective out the tips. It's effective kind of a broad side, and we'll get to a slide that kind of covers that, going out directly from the elements. But that Yagi is even more focused this way than this one. So like where my dipole might have like that, my Yagi is going to have a much narrower effectiveness. But it's going to be a lot stronger in this direction than this standard dipole is. Now there's other directional antennas that we use. And a dish is one example of this. So the dishes that you use, either that are used by like the military or whatever to talk to satellites, or the satellite dishes that we use for like DirecTV and Dish TV. They're all designed, like the ones that Dish TV and DirecTV used, they're directional, but they're designed to kind of capture everything in a certain arc. And so they position those on top of your house so that they can capture like 2 to 3 different satellites within their arc. And then taking you back to high school geometry, if you guys remember about a parabola, it's something where if anything that comes in to the parabola will bounce to a focus point. And at that focus point, they put something called an LMB, which is basically just a radio receiver transmitter. And so it can receive at that point, which will typically be, that's why you see like on those dishes, there's an arm that comes out and some little thing that like a little box or something that's facing the dish. And that's getting that signal. But that's another form of directional antenna. Now what do I mean by directional versus omnidirectional? Well, as I was just kind of talking about, so these ones and the dipole, the basic dipole, there are good examples of an omnidirectional antenna. So this antenna, when I transmit, is sending out electromagnetic radiation this way, and that way, and that way, and that way. Basically around the whole cylinder of this antenna, it's going all directions, all 360 degrees around this. When I start putting those elements in front and in back, I'm limiting not just what's coming out here the side, but I'm also making it so that what's coming out the top. So if I have an element here and an element there and an element there, like on the Yagi, then there's not as much power coming up this way and down this way. All that power is being concentrated on this plane right here. So many omnidirectional antennas can be made to be directional. But the key difference there is that, yeah, if I'm just using an omnidirectional antenna, I may not have as much power or receiving power or transmitting power, but I'm transmitting in all directions. Or at least all directions except for this higher and lower direction. But with the directional, I'm making some sort of a trade-off to limit my power going out other directions, to make it so I have more power going in a specific direction or specific directions. Any questions on these antenna types? Okay, polarization. So, broadside, we just kind of talked about this, that off of a dipole or off of a vertical or a rubber duck, your strongest is basically, think of it like a pirate ship. The pirate ship's got might have guns on the bow, but it's got a whole bunch of guns along the sides. And so they're constantly like in a battle. If you were to watch any of these movies like Horatio Hornblower or like Master and Commander or things like that, they're constantly trying to like get themselves, when they want to shoot, they want to turn their whole boat so that it is facing the side with all the loaded cannons at their target, because they want the greatest chance to hit their target. So part of this is the polarization, right? So if I'm transmitting like this vertically, with vertical polarization, I've got a much better chance of the other person holding their radio, if they're holding it straight up, of it hitting theirs. Because more electromagnetic radiation is coming off at this, on this kind of vertical direction. And vice versa. If I go like this, now like my pirate ship decides that it's going to go directly head on towards the other ship. I may only have one or two guns to bear, but maybe I do that because they've got their whole broadside coming to bear on me, and you get less exposure, right? So what's going to be the more effective? To always be at the same polarization as the other stations that you're trying to talk to. So with large antenna systems, a lot of, depending on what you're doing, so for most things that are like line of sight, vertical is used. For most things that are really long distance, they tend to be horizontally polarized. Questions on polarization? So broadside versus beam. So a beam antenna is another word for one of these Yagis that concentrates the signals in one direction. Horizontal versus vertical polarization. And the questions around this are, radiation is strongest from a half-wave dipole broadside to the antenna, is kind of the statement. A beam antenna concentrates its signals in one direction. Okay, so we talked about the radio, different types of radios, and we talked about the antenna. What was the thing that I talked about that was in between the radio and the antenna, except in the case of these handhelds? Feed line. So here's a couple different examples of feed line. I'm kind of pass these over. We typically will use coax. You guys know what coax looks like on the inside? I wish I had a good picture of it.
Braided, right?
You'll have a braided outside, and then there's if you look in the center, there's kind of a single pin of some sort, right, in the middle. So you'll have that goes all the way through to the other end of the cable, and then there's some sort of insulator between that center pin or center conductor and a braided jacket around that conductor. And then there's the black
rubber around the outside. That's just one form of coax. There's other forms of coax that actually use like internal, like they still have that internal center one, but then they'll have the insulation layer, then the braided copper section, and then an insulation layer between that and the outside, because they figure that that gives them even better insulation of the signal and less loss. So this other one is twin lead. You won't really see this around too much. We used to use it a lot before everybody had cable TVs. You might remember this when you were a little kid or something, hooking up a little twin lead from your TV antenna to your TV, and there'd be little screws in the back of the TV that you'd take and plug these into. But this is just another type of feed line that you could be using. It's pretty, for the most part, except in some really kind of bare bones DIY situations, most twin lead isn't used as much anymore. Most people are using coax. And there's different types of coax. So if you've got cable TV at home, you probably have coax. But it's a different type of coax. You couldn't just use that coax for amateur radio. And the reason for that is that all amateur radio systems, from the antenna to the radio and the feed lines, are built around 50 ohms of impedance. Now, impedance is sort of a fancy word for resistance. It's measured in ohms, like other resistances, but it has more to do with kind of the signal, the ability of that, not just of the ability of the cable to transmit electricity, but the ability of that cable to transmit radio frequency RF signals over that cable. And now there's different types of coax. There's a number of different types, but the only two really that you'll see on the test are RG8 and RG58. So one of the key things about feed lines is the more copper or the more conductor that you use in them, the less and the better the insulation, the less loss over a distance. So, for you to your roof of your house, like if you've got like a console radio, a base station radio to the top of your house, is probably, could be 50 or 100 feet or whatever. Depending on the frequency that you're transmitting at, and depending on the cable type that you're using, and basically how beefy that cable is as far as conductor, that will determine like how much power you lose from the point where it leaves your radio to the point where it goes into the antenna. So there's a possibility to lose power there. Now, where does the power go? Well, it becomes heat. So that loss that you get becomes heat on the cable. So we'll get into a little bit about matches a little bit later, but suffice it to say, for whatever reason, RG8 was made with more electrical conductor, and its design has a lower loss than RG58. And that loss accumulates over distance. And there's other things that can affect it. So if one problem is all these cables, they're wrapped up in plastic and rubber, and what does that do in the sun under UV light? It dries up, it becomes brittle, it starts getting damaged. If it cracks, if it becomes brittle and cracks, then water can seep in, which can start corroding the wires inside the feed line. So you need to be careful about how you need to inspect your cables if you've got them running outside, and you've got to make sure that, try to minimize the damage that can happen from sunlight. Questions on feed lines?
So there are different types of connectors. And for the test, you basically just need to know that these exist and which ones, and these kind of facts about them. These aren't all the different types of connectors. But, these are kind of their uses. So BNC is kind of a, you put it on and then you twist it a little bit, like a quarter turn or something, and it makes it, and tightens it. That one was common, it's common, used to be more common for handhelds and for some like internal uses and whatnot until they came up with some better cables. They used to also be used a lot in mobile. The SMA, we'll skip over the SMA for a minute. This next one, the PL259 and SO239 are actually just this pair. So this wide barreled one that you see there, paired up with that. So one is the male, one is the female for that. It's right there, that just fits right onto there. So you just have to know that this one is really common for HF, and then it's mates with that other one, the 259, the 259. You don't necessarily need to know which one is male and which one is female, but let's see, let me get the mic back under control. That's still coming in okay?
I don't know, say something.
Say something?
Yep.
The next one is SMA. And you'll see that this one's smaller, a lot smaller, and is probably the most common right now for handhelds. Okay. And there's actually kind of two versions of this. Most radios will use this kind of SMA, and then the other one will use what's called either reverse SMA, or there's another term for it. What was that for the Yaesu? I mean, for the Chinese radios like the Baofeng.
So reverse one?
Yeah, it's basically where it uses, well, you can see it here. Basically, they've just swapped which it's the same connector,
Yeah.
but they've swapped it for what's male and what's on the antenna side and what's on the radio side.
They do call it reverse thread.
Reverse thread, or
SMA.
there's another like term for it. So essentially I could probably screw these together, but I wouldn't do anything. So see, it's just the opposite. And then this one you'll see mostly just for handhelds. And it's okay for most, like, most like kind of that UHF, that 2 meter, it's good enough for 2 meter, it's good enough for 70 centimeter, whatnot. But then when we get up into microwaves, there's too much loss on these other types that we've been looking at. So the higher the frequency, the more loss there is with some of these different feed lines, as well as some of these different connectors. And this, which is the other end of this, has an adapter on it, is the N style. So you notice it's got the pin, then it's got an inner sheath on it, and it's got the outer. And that's really to kind of isolate, give more insulation and isolation to both the inside pin conductor and the one that would normally be the sheath for that. Questions on these? And really, the questions are like, the PL259 is commonly used in HF frequencies. The SO239 is commonly used with the PL259. The N
type N connector is most suitable for frequencies above 400 megahertz, which we kind of consider to be beginning of microwave. Okay, now I've talked a little bit about the matches. I've said a little bit about, hey, what happens if, so we've got these things that are set up. These feed lines are all supposed to be designed so that they have a 50 ohm impedance. And the connectors on the radio are also designed so that they have a 50 ohm impedance. And the antennas are typically designed so that at their best frequencies, at their most resonant frequencies, they have a 50 ohm impedance. Now when those things don't match up at 50 ohm impedance, we get what's called a mismatch. And that causes, and the way that we measure that mismatch is through something called a standing wave ratio, or SWR. Okay, so the way to think about this is you've got your signal that's going through from your radio into the feed line and into the antenna. If I were to use, say, instead of like one of these special coaxes that are 50 ohm coaxes, if I were to use like the 75 ohm coax that I got from Comcast with my cable modem or with my set-top TV box or whatever, what would happen is as that signal leaves the radio, tries to get be transmitted onto that feed line, it's almost like there's a wall or a screen door of some sort that it hits. And that mismatch causes a portion of that signal to actually bounce back to the radio. Okay, so at low level power levels, that typically doesn't do too much harm. But the higher your power level, the more power that you're sending right back into your radio, which may not be able to handle that. It might damage some of the electronics coming into it. The same thing can happen at the feed line to the antenna. So if the antenna is like mistuned or mismatched or whatever, and you have a mismatch there, you get that same kind of thing where your transmission goes out and only a portion of it actually makes it out onto the antenna and turns into radio frequency electromagnetic waves. But the rest bounces back. Bounces back towards the radio. So ideally, if everything is at 50 ohms, if your radio is at 50 ohms, if your feed line is at 50 ohms with no loss, if your antenna, you're transmitting on a frequency that your antenna is also coming out at 50 ohms, then we call that a 1-to-1 match, an ideal match. It's a perfect match. You don't lose, there's no loss at all in your transmission. So if your radio is transmitting at 5 watts, 5 watts of radio frequency power are emanating from your antenna. But typically there's some amount of mismatch in there. Either maybe you're not transmitting at the exact ideal frequency. And that's really with antennas, there really is kind of a center frequency where it is most effective. And as you drift from that one way or the other, that match changes. That the how many ohms of impedance it's providing changes. And depending on your antenna, and depending on your system, that could be very narrow and very finicky, or it could be wide. You could have a fairly wide band that's effective for your antenna, and it won't be too much of a problem. So a lot of radios, especially radios in the base stations type, will have a built-in SWR meter that will show you this, what the ratio is. Now, what happens if it goes higher? As I said, so getting up into 2-to-1, still okay. 3-to-1, you're losing some, but 4-to-1, you're getting to the point where you're probably losing more than you're transmitting. The that turns into either heat in the conductor or damage, like power coming back into your radio, causing damage. So we consider everything above 4 to 1 to be a really poor match, and you should not, you should stop transmitting and try to figure out where the problem is. There's also an appliance that you can buy that you can stick in between your radio and the feed line, that if you know that you're gonna have a really bad match with your antenna, you can cheat electronically to an extent. You can use an antenna tuner that will actually try to bridge that mismatch so that less is lost. You still have some loss. It's not a perfect solution. It doesn't get you as in like a naturally ideal perfect 1-to-1 match, but it does limit the possibility of damage to your radio, and it does help more of the signal to get out. With one of those antenna tuners, I should have brought mine. I do have one. And then if you see like it's really erratic, like your SWR ratio is changing quite a bit, it's probably because you have some damage to your feed line, or it's not tight enough connected, or there's some other thing, like maybe there's it might be loose, or there be some damage or something on it, where it's like kind of like a short almost. Questions on standing wave ratio. It's not always, it's a hard thing to kind of describe. But any questions on that, or do you need to provide an alternate explanation there? Okay. So, talked a little bit about this. Power lines. So when you install your antenna, you should make sure that it's not going to come in contact with any power lines. One, that it's not going to be any closer to 10 feet to the power line, and especially if it falls, it won't come in contact or be closer to the 10 feet. And the reason for that is because you're giving a possible route for the electricity from that power line to arc over and go straight into your antenna, and into your radio, and if you're holding your thing on your radio, into you. Which is also a reason why we use grounding wire, or we try to ground our antennas as well. Don't attach your antenna to a utility pole, because that's just giving it one more option to come in contact with those high voltage power wires. Okay. Some people will, if you get into this hobby a bit more than your handheld transmitter, then you might decide that you want an antenna tower. If you don't want to put your antenna on top of your roof, say you have an acre or two of land, you might set up a tower. And if you do, you should do it safely. Use a hard hat and safety glasses. Use a climbing harness, and always have some sort of a helper or spotter for you when you're working on the tower, in case something goes wrong and you need help. And the same as we just talked about, stay away from overhead electrical wires with your towers. Questions? Okay, grounding. So when you have an antenna that you put on your house or outside in your yard or whatever, you should try to also install a grounding system for it. So you might, for grounding wires, you just have like those pure copper wires. You might set up one or more copper grounding stakes sunk into the ground nearby, or if you can't do it nearby, you'll want to make sure that the connections of those grounding wires to your ground site, whatever you're using for ground, are short and direct. No Sharp bends, looping, sharp bends, or whatnot. Because the reason why you have that grounding wire, for one big reason you have that is for lightning. And lightning is always gonna try to take the quickest route. And so if you put a bend in there, a strong, sharp bend, it'll just keep going to the next thing if that's electrically closer to it. So you wanna make sure that your grounding system is predictable, and the way to do that is by using a short and direct ground with no sharp bends. And you know, it's good to, you can use a common external ground for your radios and whatnot. Like I said, you can set up a ground where you sink a bunch of an array of copper rods, and then I'll set them up to you can get a grounding bar that you can put inside your home office or wherever you have your radios, your base station radios and whatnot, and connect them to that. Questions on grounding? I had a lightning strike at my house last summer, and luckily I didn't have any problems with that. I had a whole bunch of other things die. It struck a tree, which I didn't realize until now was the tree that it struck, because the tree died over this last 6 months or whatever. And when I took down the tree, I noticed this really weird, like, ripping of the bark, this vertical ripping of the bark. And at first I thought, oh, it's just like my neighbor, or maybe my cats did that or something, because my neighbor doesn't like that tree. But I saw somebody else post about a lightning strike at their property, and I'm like, oh no, that's exactly what I saw. We're still kind of recovering, replacing things like the garage door and opener and things like that all shorted out during that. But luckily it did not hit any of my amateur radio equipment. Okay, RF safety. So we talked a lot before about, we've got, you know, these gamma rays and ultraviolet rays, and those are the ones that can really harm you. Well, yes. And while we have microwave ovens in our houses, and we use cell phones that have like 100 milliwatts of power right next to our head and our ears and whatnot, and do all these things, the greater amount of power that we have coming out of the device, and the amount of power depends on the frequency, right? And remember, the higher the frequency, the smaller the wavelength, the greater the amount of power is just inherently in that transmission, right? In that radiation. But even at the lower frequencies, if you push it out with enough power, it can still be a hazard to humans. That's not an issue at like the 5 watts or 10 watts that we use here on these handhelds. And typically it's not an issue with 100 watts because we have our antennas placed somewhere outdoors away from most people. But you do have to think about RF safety, especially when you get into those larger radios with more power and larger antennas. So some of the key things here are exposure. So how close you are to the antenna and its transmissions and how long, so the proximity. And if there's, depending on the amount of power, if you're touching an antenna that's actively transmitting with a decent amount of RF power, you'll actually get an RF burn. And that can range anywhere from it can range anywhere from a sunburn style burn to a 2nd or 3rd degree burn, depending on how strong that power is. Chris, you have some experience in this category, it sounds like.
At my dad's house, he apparently was transmitting, and I just was looking at his antenna, and happened to touch it, and it woke me up, and it burned my hand. But yeah, it was
about how many?
Startling.
What band do you know what band he was transmitting on and how much power he typically had on a station?
No, but he had an amp on there, so it was. I'm not sure of the,
He's probably transmitting at more than 100
oh yeah,
watts.
and it surprised me because it was hot, but I got the shock too, and I learned not to be close to that.
Yeah, I mean, if in your kitchen you've got a microwave oven, and that microwave oven could be rated for anywhere from like 900 watts to 1600 watts. It's cooking food with that much power. It's making that food hot and all the way to burning possibly. So I mean, that's a good example right there of.
From the inside, is it inside out? Or is it
So,
outside?
I think it resonates with the water. It causes the water molecules inside there to heat up. So I think in that sense, I do think it's an inside out. But it's a good example of why you should be careful, especially as you get up into higher power and whatnot. As I said, our cell phones and these typically are not an issue for this type. Okay, so you gotta make sure that you use safe power levels, as well as safe distance from people. So if you know that you're gonna be transmitting with an amplifier at like a kilowatt, you can look up on the FCC and the ARRL.org site and find guidelines for how you should be, like how far does this need to be from my house or from my neighbors, and those type of things, based on the frequency and based on the power, and the directionality of the antenna system that you're using.
So when you say touching the antenna, I mean, does that apply to the distance to the house too?
I mean,
It's gonna fry or
No, I
soften,
mean,
face
it depends. Like you'll typically have like there'll be insulation between your antenna of some sort.
Yeah, okay.
Like it's not electrically connected directly to your house.
And
It's
you're not-
connected to the feed line, which is insulated, and then that's connected to your radio. But you do want to make sure that you're placing, like, you wouldn't like want to place your high energy antenna like right outside your daughter's second floor window or the bathroom window or something. You're gonna play it
Pets
up on
can-
top of the house.
Yeah, you don't, or pets can easily
Yeah.
get to it. I mean, you're not transmitting like a long, typically,
Yeah.
in a long period of time, but, you know, if someone goes past it, like I did, touch it, or a dog or
Yeah.
cat pees on it or sits on it, they're
Yeah.
gonna do that.
Yeah. Have one other thing about this. I was thinking about what has left me now. Yes, there's always the anecdote about the microwave technician that warmed himself up by the transmitter, by the antenna. And not a good idea.
What would happen?
No, they get burnt, RF burns and whatnot from it.
What about brain stuff?
I mean, those things are all possible. That's the thing. So there's a lot of stuff. So there's a certain level of damage, just like by the amount of power, and that power getting absorbed by the cells of your body. There are other issues around specific frequencies and we talked about this of like the energy based on the frequency. So the higher the frequency, smaller that kind of wavelength is. And I'm not a doctor nor a physicist, so everything I say from here on out is based on my kind of anecdotal conjecture. But there are certain ways that those they can resonate with things of certain sizes more, those radio frequencies. This is part of the reason why we talked a little bit about VHF versus UHF with regard to buildings. And some of that is the size of the things that are involved in a building can resonate a little bit more, or maybe absorb more of the lower frequency stuff than the higher ones. But what we get is, like, as things go higher and higher, and this is part of why gamma rays and UV and X-ray cause cancer. Because that energy, they resonate with those cells, get absorbed by the cell or the molecule or the atom, and cause them to either ionize or break apart or do something like with DNA. Like when they hit DNA, they damage the DNA. And our body's supposed to be able to like kind of detect that and chuck those cells with the bad DNA in them. But that doesn't always happen, which is cause for cancer. So all depends on what it could resonate with for the most part, in smaller amounts. And that's why they kind of say, well, you know, there's debate around Wi-Fi and Bluetooth and whatnot, right? In some circles, on if they have an effect on, say, our neurological system or whatnot. But typically it's a lower power, also a lower amount of overall energy. And they don't completely think that there's that same kind of resonance that can do that kind of damage. At least not a lot of damage. At least they haven't proven it.
The lead neurologist at the University of Utah, at the Neurological Center, is saying there's a greater incidence of Alzheimer's taking place as a result of EMF fields. And while not everyone's affected by it, there are many individuals, more and more individuals are being impacted by it. There's a clinical study going on right now, and that's what they're saying is that the lights, everything that emits EMF,
Yeah.
is
That's the problem, is they don't have targeted studies to say one frequency or another is
Yeah.
bad. But they can tell that there's maybe a trend here somewhere.
Yeah, is contributed to Alzheimer's, dementia,
Yeah.
let alone cancer.
Okay, on that cheery note, any more questions on RF safety?
Just for what it's worth.
Okay, so now we're gonna get into atmosphere. So we've only got about 20 more slides left. But we're gonna get a little bit into how propagation works. So the Earth, we talked a little bit about this before. You guys got everything you needed off of this, hopefully. But we live in what's called the troposphere. So it's the area of the Earth that sits between the surface of the Earth and where all the breathable atmosphere is. So like when you get up to like the top of Mount Everest, you're getting to the edge of the troposphere because there's not quite enough oxygen there for people to live properly. And to be able to breathe and get all the oxygen that they need in a breath, and that applies to other forms of life as well. And the pressures and all those things just don't quite match up for living healthfully. And around that, then what we've got above that is the rest of the Earth's atmosphere has less pressure and still has the gases, and different gases kind of accumulate at different levels and whatnot. So you still have oxygen, O2 oxygen, you still have CO2, you still have N2 nitrogen and carbon monoxide and various other gases that compose our atmosphere. And as they go up, we got up into an area of what we call the ionosphere. Do you guys remember what the definition of the ionosphere was? We talked about a few weeks ago. Was it last week or the week before?
Just the layer that protects us from the rays of the sun.
Yeah. And the way that, how it's formed is we've got a couple things going on. One, we've got an atmosphere. We've got gases that are trapped by gravity into the atmosphere of the Earth. The other thing is that we have a dynamically magnetic core to the Earth that also has some effects here. And what happens is
So we have the Earth. We've got the core of the Earth, it's, you know, whatever, North Pole and South Pole. And we get into this thermosphere and exosphere, so the ionosphere. Which is basically all those gases in our atmosphere. But what's happened is the sun and other cosmic rays are hitting them and hitting all those gas molecules and breaking them apart. Either breaking the molecules apart into separate pieces or taking those atoms and giving them enough energy so that their electrons get separated from their nucleuses, making them all ions. So an ion is a charged particle. It's a particle, either a molecule or an atom or an electron. It's a particle that has a positive or negative charge. Now we typically will see these things as like, you know, a proton has a positive charge, that's part of the nucleus of the atom, and an electron, the tiny little particle that orbits or somehow, you know, is intertwined with that nucleus, has a negative charge. And so what will happen is one of these cosmic rays, or rays from the sun will come in, overexcite that molecule or atom, and cause one or more electrons to take off, or cause the molecule to break apart and become two ions, or two unbalanced charged atoms. That creates, so then going back to your physics and electronics, any sort of particle that has a charge that's moving creates an electric and magnetic field. So you've got all those things combined, all those electromagnetic fields of those individual atoms and molecules that have been hit by solar or cosmic particles, or solar or cosmic rays, all moving around up there, and they're combining to create this huge electromagnetic field around the Earth, which we call the ionosphere. So what does that mean? So what is the effect of that? Well, further charged particles coming in get redirected by that magnetic field, by that electromagnetic field. They move, they stop going straight, and they're redirected in a different direction. Many of them are redirected away from the Earth. So in that way, it protects us from the majority of all these gas molecules and gas atoms are protecting us from the vast amount of high energy particles coming from the sun and elsewhere. It so creates this kind of security blanket of a sort. What's something that Mars does not have?
An atmosphere.
Doesn't have an atmosphere, doesn't have a magnetic core anymore, so it doesn't have an ionosphere. Now it's farther away from the sun, but when Mr. Musk and company make it to Mars, they're gonna have to take that into account. Because it's something that we're protected from here. They're gonna have to find a way, either living underground, using like, you know, one or two, like a meter deep water shields around their habitations or whatever to absorb all that cosmic energy, or for that solar and cosmic energy that's hitting Mars, so they don't come home with cancer. Okay, so how does this affect us as far as radios? So I mentioned, okay, so it protects us from all this stuff coming from the sun and from the rest of the universe. It also affects our own radio emanations from the surface of the Earth. And that depends, the effect that has depends on what frequency we're transmitting at. So when we're transmitting at HF and below, and the very lowest portions of VHF, which, what were those frequency designations for those again?
What was HF defined as last week? How many megahertz to how many megahertz?
33 to 30.
3 to
megahertz.
30. And VHF was defined as what? 30 to what?
300.
Yep, 30 to about 300. Those each have a different effect in some of these. Now, another thing that happens is, so scientists have kind of, and radio users have kind of classified these segments of the ionosphere. They've given them letter designations, D, E, and F, and actually they divided F into F1 and F2 for how far they are away from the surface of the Earth. And they each have different characteristics. So, when do you think a particular spot on the surface of the Earth receives more radiation, and therefore, well, yeah, what time of, how often and what time of day do you think the ionosphere is strongest in a location?
2 p.m. in the afternoon.
Okay, so daytime, right? And why is that?
I don't know, I just guessed it.
Sun's up.
The sun's up. The sun's actually actively shining on that segment of the Earth. And so when it's most during the daytime, when the ionosphere is most active, all these layers become active, all the way down to D. And each of these layers kind of has a different, you don't need to know each of them specifically, but they each have a different characteristic for what radio frequencies they absorb or bounce or allow through. Okay? So, and typically, the higher the frequency, the smaller the wavelength, the higher the frequency, the greater the chance that radio signal can make it out of the ionosphere. Okay? But what we might call the minimum usable frequency or whatever, sometimes like changes throughout the 24-hour clock. And during midday, you've got this D layer that's one, lower down, and two, absorbing a lot more of the frequency spectrum. As things become night, as we get into this transition from day to night, the D layer disappears. It's no longer receiving direct sunlight, so all those gas molecules are not as active, or those, basically that electromagnetic layer goes farther away, and we have just the E and the F. But right here we get kind of two distinct versions of the F layer.
So does that mean it's easier for transmissions at night?
Well, we'll see how that affects things. We'll talk a little bit more about that. So, troposphere is the lowest. It's where we live, it's where we do most of our transmitting, so we transmit from the troposphere. Sometimes troposphere to troposphere, but often like troposphere into the ionosphere. The ionosphere is what propagates the waves for the most part. And there's kind of a couple different ways that does that. So, and basically what the question is what frequencies get out, so with this, it's always a question of which frequencies will get bounced, which ones will get absorbed, and which ones will actually make it through that layer of the ionosphere. And those and we choose our frequencies and the time of day that we transmit based on those characteristics. So first of all, there is a way within the troposphere, and this is caused by the difference between layers of cold and warm air, to do what's called tropospheric ducting. So tropospheric ducting basically will get some level of kind of the bounce back effect just off of that just off of whatever electrical difference there is between that cold layer and that warm layer. Chris,
I have direct, experience with that.
good.
I was at a portable unit that, HF unit that I was, camping with scouts up in the high units. And it was a 100-watt, transceiver with what's called a whip antenna. It was about 15 feet high. And at night, probably at 9 p.m., I'm going through the bands trying to find someone to contact, and I hear someone from, has everyone heard of New Caledonia? Way out there in the Pacific. And I was able to, 6,500 miles away, and I was able to contact him on that radio, which just, the hand gods were with me that time. 'Cause
So
that
not completely,
usually-
that one was tropospheric ducting.
You wouldn't have been?
No,
Then I'm wrong.
but that gets us into the other ones.
Okay, then which,
So tropospheric ducting is really like you're bouncing off the weather layers.
okay,
So it's lower, and it can have this effect of like kind of going down and then hitting the ground again and coming back up into the weather.
okay.
And
So-
it's a way for you to get some transmissions
Oh,
around 300 miles.
sorry, I misread.
That's
that.
okay.
So, okay, keep going then.
But then when we get
I'll
into, so
I'll
on,
spread it.
so sporadic E layer, so remember the E layer was right there in the middle. So you might have heard me say like, oh yeah, we don't have very strong, so like the top of HF, so at that 30 megahertz, into 150 megahertz, we're 2 meter and 6 meters at 50 megahertz. We can sometimes, by transmitting near where twilight is, or dawn, we can hit the E layer that's super excited still from being partially in the sunlight. Does that make sense? You've got the D layer that's slowly going away because the darkness is coming, but the E layer is still somewhat powerful because it's those molecules and gas molecules are still cooling down during dawn or during dawn they are starting to get energized, and during sunset they're still kind of coming down in their energy levels. We can sometimes get a sporadic E layer over the horizon propagation, where it literally hits that E layer and bounces. Now with 6 meter and 2 meter, most of the time it's going to go straight out through the ionosphere. But in that case, if it's just being held back by the F layer, but at the E layer, we can get a significantly powerful E layer can have some of that bouncing effect. So it allows us to communicate on those higher frequencies of 28 megahertz up to 140 megahertz, 145 megahertz, and have some of that same sort of halfway around the world kind of effect in transmitting. And saying 10 meter signals are best during the day during high sunspot activity. So 10 meter signals are really good at bouncing off that D and E layers. Now what he was getting into, let's just come back to, so when he was transmitting, and do you know what band you were on?
I would do 20 or 40. I'm trying to find when exactly that. This makes more sense then. Yeah.
It was able to bounce off of lower frequency than 10 meter. It was able to bounce off of these layers, these E and F during the nighttime, and make it farther around the world. And you literally actually, in some cases, on the right paths, you can actually
Oh, yeah.
get your own signal back all the way around the world. It comes in as an echo later, but it'll go, along a great circle, depending on what its directionality is, it will go along a great circle around the whole Earth and come back to you. So your direction, this is why people that are in HF use directional antennas, because they're trying to get like, hey, I want to make contact with somebody in New Caledonia, right? Or in the Falklands, or in, you know, South Africa or whatever, and they will find like, and they'll actually check, some of them will check and see, is my propagation better this direction around or the other direction around? And sometimes they will take the long way around to get to try to target a specific country, because for whatever reason, the electrical properties of the ionosphere are more favorable to them along that. And actually what a lot of people do is, there's a lot of really powerful opportunities for long-range communication right here along sunset and sunrise, as you have kind of things on the cusp. But they're, you know, as it mentions, like during the day, you can use 10 meters to good effect. To do, you know, long distance, you know, greater than 300 miles or whatever here in the, you know, here in the United States or maybe in some of the nearby countries. Each band kind of has its own characteristics for how it interacts with this. Questions on those before we get into electronics for 30 minutes? Go ahead.
I had a physics teacher.
I'm not a physics PhD, so.
But he was big in ham radios, and I remember, and this is 50 years ago, you talk about talking to people in Australia or something, I swear, I remember a term, skip wave, is that?
Yep.
Is
That's
that
what we're calling that when it's bouncing off, back and forth off the ionosphere and back onto
So
the
that's
Earth
what they
and back
call it,
onto the
skip
ionosphere.
wave, it's skipping, okay.
Which also means that I mean, there's all sorts of ways that you can get technical about this, right? Your angle's gonna make a difference, and there's gonna be areas that are gonna be that have less chance of hearing you than others because of where your signal's coming down. So the geometry of
So
that,
he
almost
uses
like a pool
directional
table.
antenna,
A directional antenna,
You try to-
possibly at a specific angle and all that. Just like you would do the geometry on a pool table
okay.
to hit, you know, to bounce
Maybe
off
an
of this wall.
amp-
Huh?
Maybe an amplifier.
Yeah, or a cheat with by throwing more power at it, more money and more power at it. But there are people that like go with you know 5 or 1 watt to 10 watt radios, and they've made this an art to an extent of making these, you know, getting really good antennas that they can and whatnot, or really good placement, like sitting on top of a peak, and making the same sort of contacts around the world by optimizing on those other factors rather than power. Okay. I think we're gonna still hit about satellites here later, so I'll skip those. Extemporaneous comments. How many of you have ever looked at an electrical diagram before? Okay, we got one. So we're just gonna learn a few of these. So there's 1 or 2 that can be on the test. And these are the 2 figures that could possibly be on the test. And basically what they'll do is they'll say, which of the following is a resistor? And the answers will be 1, 2, 3, 4, or 5, or something like that. So 1, the resistor. So a resistor is an electrical component that provides resistance. It basically takes the electrical energy that's coming through that component and turns it into heat. So a resistor is typically, I think a really good way to think about this, and I don't want to do this to confuse you, but think about the old school light bulb. What's in the old school light bulb? You see 2 wires going up, and then what's that in between?
Filament.
A filament, which is an even narrower piece of wire that's kind of in a circle somehow, you know, like almost a coil, but it's stretching in between those 2 points. And what's happening is, because it's a very thin piece of wire, it's providing resistance. And it's absorbing so much heat because it can't really take the full 120 volts across it, that it's turning all of that into heat, and all the way up so much heat that it becomes light. Does that make sense? So it's not just, so at smaller levels, it's putting off a little bit of IR radiation, infrared, but as you put more and more electricity through it, more and more voltage across it, more and more amps passing over it, it actually gives out light and glows. That is a resistor. Now, there are lamps that are also that on here that are resistors. So I only give you that example of a resistor because it's something that you all have experience with. I don't know, maybe she's only seen LED or compact fluorescence in her lifetime. But if you were actually look at the component, it would be like a little piece of wire that actually has smaller wire in between, and then some sort of a ceramic or something covering that to absorb all the heat that's being given off by the electricity moving through it. So you use that to kind of bring down the voltage of a circuit to where you want to use it. Because you may have other components that have certain input voltages and whatnot that you can't exceed, or else you might damage them. The next on here is the transistor. It's this thing in the middle, this circle. And the way to understand a transistor is, it's actually, a transistor is sort of like a switch. It's an electronic switch. So it's connecting, in this case, we've got a battery that's connecting to a lamp. So we got a battery going to the ground, and we've got this transistor in the middle going to the ground. And so this kind of comes in here, and if this transistor is set to on, then the light turns on because this is actually connecting right here.
So that's our switch.
Yeah, it's somewhat of a switch. So, and how that is if it's coming in right here. So in this case, we've got a switch, an actual switch right here, feeding into this resistor, and then feeding it, so the resistor is kind of bringing the circuit into a proper input voltage for this feed into the transistor. And if there's electricity passing along here, it makes it so that this one can go through. If there's no electricity passing through here, then it stops there. So this piece and the diode are pretty much what all digital electronics are built on now.
So the transistor is the same as the diode?
Transistor is a extension, let's say, of the diode. It uses some of the same kind of semiconductor technology.
So the diode is the earlier technology, the transistor?
We still use them. We still use diodes. And we'll get into those in a minute. But the idea is like, so in your phone, in the middle of your cell phone, in your tablet, in your computer, is a chip that contains millions and billions of microscopic transistors in a specific array that allows it to do computational operations by just flipping on and off switches, essentially. So it's kind of the basic. This is also why, like, you ever heard the phrase transistor radio? Some of you that are older. And what did that denote? It denoted an FM radio.
Yeah, wasn't it?
No, the AM ones you could do with just a coil and
Yeah,
a
I
crystal.
remember the coils with it.
Oh, yeah.
But transistor is almost necessary to do frequency modulation. So FM radios were referred to as transistor radios for a number of years, or radios that included FM, I should say, were considered transistor radios. That was kind of a name that was used for them. Where now, like, all radios are done with transistors, so it doesn't matter. But, okay, so the lamp we talked about a little bit as an extension of the resistor. The battery, this kind of represents the cells of a battery. And lastly, ground, which is this funny looking E on its side here. And what's the function of ground? It's the place where all electricity wants to fleet to, or maybe fleet from, I don't know. Whatever. Some people say it's a push, some people say it's a pull. Okay, any questions on those 4 or 5 components before we move on to the next ones? Okay. This is the other one. Let's talk about the ones that are on the test. Number 2, a fuse. What does a fuse do?
Basically, a point where if it gets so much power,
Yep.
it'll blow.
If more amps than it can handle pass through it, it'll blow. So it will it won't, it's not that it will resist, it's supposed to allow it to go through until more than it can handle goes through, and then it's designed to blow. And why would you want that?
So it doesn't fry everything in your
Yeah,
radio.
because most components in an electrical circuit have some sort of sensitivity to how much current they can handle, or how much voltage they can, a voltage difference they can handle. Number 8, the LED. Okay, let's skip. Let's start with 5. 5 is the diode. Okay, so the thing that makes transistors and diodes possible is the fact that we discovered that we could somehow electrify or take something like sand, like silicon that's not a conductor typically, but we found a way to taint it to make it a conductor, but only under certain circumstances. And in the case of a diode, the silicon or whatever non-normally conducting, what we call semi-conducting materials, are designed only to allow electricity through in one direction. Which is why you see it's an arrow. Okay? So that's why it's also called a rectifier. Because in a sense, it only allows current through it, and it rectifies the current to only come in one direction, or only move in one direction. Now, moving over to 8. Looks like the same thing, except for it's got these squigglies coming off the side of it. And these are kind of to denote that it's like, it's emanating. It's a light emitting diode. It's emitting light. So it's just a diode like that one, except for it emits light. Number 6, the capacitor. So a capacitor is basically, it's an electrical component that has 2 plates, 2 sides. And so electricity comes into one side and creates a field. And when that field gets sufficiently powerful enough, those particles can actually jump that gap between the 2 plates. You can charge a capacitor and actually disconnect it from the circuit it's in, and it will still have that charge on it. And if you're really a jerk, you can take that capacitor and poke your friend with it and shock them, depending on how much energy is stored in that capacitor. But so you have that here is these 2 plates, one plate that's kind of curved and another plate. Transformer. We didn't talk about this earlier, but if I take away everything but that, where you just have that kind of thing there, that denotes a coil or an inductor. Okay, so this is what So basically, somebody determined that if you take an inductor here and an inductor there and put something in between it to kind of bridge the electrical fields between those coils, those inductors, that you can create a transformer. So depending on how many turns of wire you have on one side versus how many turns of wire you have on another, you can change the voltage on either side of that transformer. Where's my basket? Where's that? So, like,
What's the things on all telephone poles?
well, so for example, right here, this is a transformer, or there is a transformer in this little thing that you have. The thing I use that Chris is using to charge his computer has a transformer in the middle of that to take the power going from 120 volts and turn it into something like more like 19 or what is it, 25 or something like that, depending on the laptop.
So then are a transformer and an adapter just the same name for
It
There are
is.
different names for the same thing?
Sort of an adapter, but it's an electrical adapt. It's adapting the. So there's kind of two ways. So if I have something that wants to work, I've got a wall outlet that works on 120 volts, and I've got an item like a phone or something else that works at a lower voltage that can't handle it. If I just plug that 120 volts into it, it would just fry it.
Mhm.
There'd be too many amps moving through it and whatnot. It would just either explode or start burning or something. I don't know. So there's two ways to get there. One way is to put a whole bunch of resistors to eat up all that extra voltage and some of that current, and then plug it in. But the more efficient way is to do this where you've got these two coils right next to each other, and where on one side it will be like 120. So on this side, what is that, number one? I didn't define number one. But say this is the wall. Say this is the wall right here, and it's 120 volts, 120 volt circuit with however many amps go along with that. And we move it down here to like say 30 volts or 20 volts. But actually, because we don't lose anything, there's a different proportion of amps in that. So we brought down the voltage, but we may have increased the amperage in that. So it typically, unless there's loss here, which there most definitely is, because how many transformers have you actually felt like when plugging in are always hot? They're always running hot somehow. So there's some certain amount of loss there in the circuits that are used. But basically it's used to transform the voltage along two sections of a circuit.
And the one on that diagram on T2 is different than one on T1.
Right. Because these are different diagrams and different questions that go along with them.
Okay.
So they're not supposed to correlate between diagrams.
Oh, I'm just looking at the
Yeah.
the graphic legend. It's not the same as what it was before.
Yeah, those, but the symbols that go along with them. So if you were to look, number 7, if it hadn't defined here, that would still say resistor. Which brings us to this one, number 9, the variable resistor. So in any kind of circuit where it's trying to show that it's variable, you'll see this kind of arrow back onto itself, which means it's somehow adjustable. And there's different components that can be variable, like there's such thing as a variable capacitor, there's a variable inductor, like that crystal radio set that we were talking about a few minutes ago, that essentially was a big variable inductor. Because where you would tap that coil was variable, and that would make it different and allow it to tune in to different frequencies.
I've been sitting here for the last 10 minutes trying to figure out what that radio was called.
Yeah.
Crystal radio.
Crystal radio, yeah. But you'll see that same kind of arrow back on itself symbol anytime it's a variable.
Yeah.
Okay, so what have we not done? Single pole, single throw switch,
That same physics.
number 3.
Oh, yeah.
So as you see there, it's just an open and closed gap right there for a flip switch. Or in your old electronics physics classes, you might have actually had one of those little things that's like on a hinge or whatever, and like bridging two two sides of the circuit. What have I not covered here? Another word for that variable resistor is a potentiometer. Because I guess depending on how much resistance you apply to the circuit, you're changing the potential. You're eating up more or less volts on that circuit. Changing the potential energy on that circuit. Questions? Okay, now we got our last one. Our variable resistor, variable capacitor, and our antenna. So that arrow sort of back onto itself. The variable capacitor. Remember two plates for the capacitor? One of them is not curved in this way, like the other one. But two plates and then the arrow coming back on itself mean that it's a capacitor that you can change that capacitance by some dial or some other method. Arrow back onto itself on this inductor, this coil, a variable inductor. This, which we don't have defined here, is like a signal source. So this is essentially a really basic radio. And the antenna. The antenna is this kind of upside down triangle up in the air. So we have a signal coming in, we change the inductance, the capacitance on either side of here, and we change the inductance on this other part of the circuit, and that all combines together to be a radio, to actually transmit or receive. Questions on this figure? Okay. Volts and amps.
Did you get that done?
No.
Can you go back for a second?
Sure. I talked too much today. I'm actually like 20 slides shy. You're gonna have to come next time just to get everything, not just to answer questions. Okay, any more questions on this one or still? And remember, these slides are also available in that email. There's a pointer to the slide deck. But I know that actually writing it down does help
I got it.
in learning. Okay. Volts and amps, just to kind of give you an idea. We're all familiar with batteries, right? All these type of batteries from DC, AA, AAA, quadruple A, which you'll now even find, not disregarding the ones at the bottom. They are all 1.5 volts. So what's the difference between them? Their size is different, right? D's are big and fat, and AAA's and quadruple A's are like skinny as a pencil. What's the difference if they all say they're 1.5 volts?
The amps.
The amount of amps, the amount of electricity that they can store on them. So the bigger the battery, right? The greater the amount of milliamp hours it can supply. Then you got your 9-volt and 6-volt battery. But what I was trying to point out by bringing this to this thing that we've all got some experience with, right? Of batteries, of these cylinder cell batteries, is understanding what that's different. So what are the kind of things that typically have like a big D cell in them? A boom box, what else?
Flashlights. Big-
Large flashlights, right? And what's the difference between, besides the weight, what's the difference between a tiny flashlight that just has like one AAA battery in it and the big long one that you could use as a bludgeon that's got all D cells in it, that's got like 6 D cells in it?
The brightness.
Yeah, it's a whole bunch brighter, right? Because you have more current to push through that circuit until you kind of wear out the voltage of the battery. Okay, Ohm's law. So here's another one of these circle diagrams. But we've got this up here. Is that the potential energy or volts, energy in volts, is equal to the amount of current, I, measured in amps, times the resistance in ohms. So simplifying that again to this kind of circle ratio diagram, if I know the amount of ohms and I'm looking for the amount of current, then I just take the resistance, the ohms, and divide them into the voltage. Or vice versa, if I don't know the voltage, then I multiply the current times the resistance. And this is kind of to give you a little idea, this is a little cartoon that gives you an idea of what these things really are. So amp is actually the unit of electricity moving through the wire or pipe or whatever. The ohm is causing resistance by squeezing the pipe that it's going through. The volt is kicking it in the butt as kind of the energy pushing it through the circuit. Questions on this? So we have volts, so we're measuring potential energy in volts. We are measuring current in amps or amperes, and we're measuring resistance in ohms.
Why is that? What does the I represent? I mean, R obviously it represents resistance. E represents.
I think it has something to do with quantity and it's, aside from math people making these decisions and physicists making these decisions decades and decades ago.
I'll tell you why.
Why?
Because Google says. It says that it originates from the French phrase intensité, or
Well, there you go.
current intensity.
Can they just put
Leave
a C?
No, because that's the speed of light.
Oh, that's true.
Current intensity is often referred to the phrase current.
Yeah.
And is
Well,
voltage,
French
is that
people.
like energy? Has to mean.
Voltage is like potential energy. It's where, like I said, if you're standing at the top of the waterfall, you've got the greatest potential energy. The minute that you jump off or dive off, hopefully into a pool,
Right.
you're consuming that energy, or it's becoming physical energy in how you hit the water
Right.
at the bottom of the waterfall. But the potential there, so like the 9-volt battery, the one with the little snaps or whatever, has a greater potential energy between its poles than say any of those D through quadruple A cells.
Yeah.
Okay. So we just kind of talked about this before, and here's a couple of questions on it. I'll kind of leave those to you to figure out. Notice these are kind of all done in like with a, or at least the first one is kind of your standard household thing of 120 volts. So if you have like a light bulb that is somehow 12 ohms or whatever, provides 12 ohms of resistance, 10 amps are passing through that. The next one is the power law, and this is pi, not pi the 3.14, but power is equal to that intensité, current, or whatever that was from French, the I, times the voltage. So this is how they're getting like, so they know that like, so coming back to this question over here, 10 amps times, so we have 10 amps times 120 volts. We have 10 amps and 120 volts. We come over here and that becomes 1200 watts, right? Take that current and that voltage, that 10 amps of current, that 120 volts of of potential energy, multiply them together and get 1,200 watts. So this is getting us down to our power bills, to helping us to understand our power bills. So this is why when you go in your house and you get lower voltage or lower, or those better light bulbs or whatever that don't last as long as they say they will, supposedly you consume less power. They use less wattage, or they consume less wattage, supposedly giving off the same amount of light as the analog incandescent version. So same type of thing, 10 amps, we talked about that one. We can, if we have the watts and the volts, we can determine the how many amps. So we might be able to determine like how big of a fuse we might want to put on that circuit. And if we've got the watts and the amps, we can determine how many volts. Okay. Do you guys want to press on, or do we want to press on for a few more minutes and finish up the slide deck? Or would you rather we just cover the last 15 next week? And then continue on some of our review, answering whatever questions you guys bring.
What she says.
Yeah, leave it up to her. Our fate all hangs in your balance. Okay, finish next week? Okay. Okay, as we kind of finish this up, I mean, the next kind of stuff is, that's kind of it for electricity aside from safety, which, surprise, electricity can kill. But we get into a little bit more safety and we get into a couple of other areas, but it's just, and then a little bit more about what to expect on the test. So with that, we'll close up this time and we'll finish it up next time and bring any questions that you've got. So please take the time to go through, at this point, just start going through all the, going into hamstudy.org and going through all the full, using the full breadth of all the things. What happened to those?
Right here.
Pushers? Yeah, take one of those if you haven't connected to HamStudy yet. Grab one of those flyers. It will, if you want.
We did the technician.
Yeah, there's the technician one too. And did you ever find the email? No.
No, I didn't come look at what I wrote down. 'Cause I
Okay.
thought I had
Well, I can just send it. I can just put it in my thing, and you can put in the email address the way that you want it,
Okay.
and send it to you.